The manufacturing process of copper tubing begins in the mines, where copper ore is extracted and then refined in industrial facilities. The goal is to obtain copper that is 99.9% pure, in line with international standards. Melting and casting. The process starts by loading new or recycled copper into a melting furnace. Gas burners heat the metal to temperatures above its melting point, 1083 degrees Celsius. The molten copper then flows through channels and is poured into a water-cooled mold to form billets, solid cylindrical bars approximately 10 meters long. This rapid cooling solidifies the metal quickly, and the chemical composition is tested before each casting to ensure quality. Once cooled completely, the billets are removed and cut into manageable sections weighing around 450 kilograms. These billets are then ready for the next phase of the transformation process. Extrusion and tube formation. The billets are reheated to around 850 degrees Celsius and placed into a hydraulic extrusion press. This machine transforms the solid billet into a hollow form by forcing it through a die, while a needle inside shapes the internal cavity. The extrusion process uses pressure of up to 3,150 tons, producing a tube roughly 15 meters long. This newly formed tube is rapidly cooled to prevent oxidation, marking the only hot-forming step in the entire process. Subsequent processes are performed at room temperature. The extruded tube undergoes cold rolling, where it is passed through conical grooved dies and over a mandrel to reduce its diameter and wall thickness. The result is a significantly longer tube, often exceeding 120 meters in length. The tube then goes through a drawing process to achieve its final dimensions. It is pulled through a die and over a floating mandrel that precisely shapes the outer and inner diameters. Depending on the diameter, drawing speeds can range from 800 to 1,000 meters per minute. For instance, tubes with a 14 millimeters diameter can reach up to 1,200 meters in length. At this stage, the copper is in a hard-drawn state, meaning it is strong but less flexible. To make the copper tubing suitable for various applications, it undergoes a final finishing process. Tubes are straightened and cut into specific lengths or wound into coils. If coils are required to be flexible, they are annealed, heated in a furnace at around 450 degrees Celsius to restore malleability. After cooling, the coils are wrapped in plastic film for protection and packaging. The use of copper tubing in construction has grown significantly since the 1930s, largely due to advances in metallurgy and the inherent advantages of copper as a material. Its excellent performance when in contact with water, resistance to many chemicals, and natural antibacterial properties have made it an ideal choice for piping systems. These characteristics not only ensure durability, but also contribute to maintaining the hygiene of plumbing systems by eliminating harmful microorganisms. Copper is highly malleable, making it easy to shape and install. It can be brazed and welded effectively, and it responds well to both cold and hot working processes. As a result, copper tubes are widely used in a range of building applications: hot and cold water distribution, central heating systems, underfloor heating, domestic gas supply, medical gas lines, and refrigerant transport. Copper tubing for building applications must comply with strict standards. In Europe, the EN 1057 standard defines the required specifications. In France, the NF Tube Cuivre label ensures compliance through rigorous third-party certification. This guarantees that the copper tubes used in construction are reliable, durable, and safe. The design department provides advanced engineering support using CAD software, simulation tools, and technical expertise to develop, optimize, and customize electric machine components and systems tailored to client requirements. The laminations department specializes in producing high-precision stator and rotor laminations using advanced stamping techniques, ensuring minimal core losses and optimal magnetic performance for electric motors and generators. The welding department performs high-quality manual and automated welding processes, including MIG, TIG, and resistance welding, ensuring strong, precise joints for mechanical structures and components in electric rotating machines. The toolmaking department designs and manufactures precision tools and dies essential for stamping, machining, and custom component production. The machining department is equipped with state-of-the-art CNC and conventional machines, enabling high-precision manufacturing of complex components for electric rotating machines. Skilled technicians handle turning, milling, drilling, and grinding processes with tight tolerances to ensure dimensional accuracy and surface quality. The department supports both prototyping and large-scale production, working with various metals and alloys. Rigorous quality control and in-process inspections are integrated into the workflow to guarantee reliability, performance, and compliance with exact customer specifications and international standards. The machining checkup process ensures dimensional accuracy and surface quality through precise measurements and inspections using advanced metrology equipment. The winding and assembly department is responsible for the precise fabrication and integration of electrical coils and mechanical components in electric rotating machines. Skilled technicians perform manual and automated winding of stator and rotor coils using high-quality copper wire, ensuring consistent tension, insulation integrity, and optimal electrical performance. The process includes slot insulation, coil insertion, forming, and impregnation with insulating resins. Following winding, components undergo careful assembly, aligning mechanical and electrical elements to exact tolerances. The department handles various configurations, including custom and high-output designs, with a focus on reliability, efficiency, and long operational life. Final assemblies are subjected to thorough inspections and electrical testing to verify performance. This stage is critical for delivering machines that meet rigorous industrial and customer-specific standards. The test field ensures all machines undergo rigorous functional testing, simulating real-world conditions to verify performance, safety, and compliance with standards. The paintwork department provides durable, high-quality coatings to protect against corrosion and enhance the visual appeal of components, using advanced techniques for uniform finish and environmental resistance. Finally, the dispatch team efficiently handles logistics, ensuring timely packaging and global distribution with careful coordination to guarantee the safe delivery of products to customers. The production of copper rods and busbars is a precision-driven process carried out in a specialized copper processing workshop. Utilizing high-quality raw materials, the facility ensures consistent output of premium copper products that meet industrial and electrical standards. Each month, the workshop processes approximately 800 tons of copper, primarily in grades M00 and M1, which are known for their high purity and excellent conductivity. The copper is melted and cast under controlled conditions to produce billets, which are then subjected to rolling or extrusion, depending on the desired end product. For copper rods, the material is typically hot rolled or continuously cast into diameters ranging from 8 to 25 millimeters. These rods are widely used in wire drawing and electrical applications due to their uniformity and superior surface finish. In the case of busbars, the process may involve extrusion, rolling, and precise machining to achieve the required dimensions and mechanical properties. The workshop manufactures both soft and hard busbars, with widths of up to 250 millimeters, catering to the needs of power distribution, electrical panels, and switchgear industries. Quality control is maintained throughout the process to ensure that all products meet stringent mechanical, electrical, and surface finish requirements. The advanced equipment and experienced workforce in the copper processing workshop allow for efficient and reliable production, making it a key contributor to the copper industry's supply chain. Enables precise, automated reel positioning for efficient loading and unloading. Maintains consistent line speed, optimizing performance and product quality. Ensures secure, automated pintle engagement for safe reel operation. The automatic safety cabinet provides enhanced operator protection through intelligent interlocking systems that halt machine operation when doors are opened. Equipped with sensors and emergency stop functions, it ensures a safe working environment while maintaining accessibility for maintenance and monitoring. The practical loading system is designed to simplify and speed up the reel loading and unloading process, significantly reducing downtime and operator effort. With its ergonomic structure and user-friendly interface, it allows for quick alignment and secure clamping of reels, minimizing the need for manual adjustments. The system integrates seamlessly with the motor-controlled pintle movement, ensuring smooth transitions and accurate positioning. Its design also enhances safety by reducing operator exposure during reel changes. Ideal for high-throughput production environments, the practical loading system boosts overall operational efficiency while maintaining consistent performance and reliability in demanding industrial settings. The dynamic air socket ensures quick, secure pneumatic connections, enhancing system flexibility, reducing setup time, and improving operational reliability. The high rotation speed feature of the BOST series rigid Strander line is engineered to deliver exceptional performance in demanding production environments. By enabling the stranding cage to operate at elevated rotational speeds, it significantly increases throughput without compromising precision or product quality. This capability is essential for large-scale cable manufacturing, where time efficiency directly impacts productivity and cost-effectiveness. The system incorporates advanced balancing technology and robust mechanical design to ensure vibration-free operation, even at high speeds. Additionally, intelligent speed control mechanisms monitor and adjust rotation in real time, maintaining stability and consistent tension throughout the stranding process. This high-speed functionality not only enhances operational efficiency, but also ensures smooth, continuous performance in both light and heavy-duty stranding applications. Manufacturing process of electrical cables and wires at Havells, India. Alwar Plant Havells India Limited, one of the country's leading electrical equipment manufacturers, operates a cutting-edge cables and wires manufacturing plant in Alwar, Rajasthan. The manufacturing process begins with the procurement of the purest raw materials from reputed suppliers. These materials undergo stringent mechanical and electrical tests to confirm their quality and suitability for cable production. The next stage is wire drawing, where large copper or aluminum rods are reduced in size from 8 mm to as small as 1.6 mm. This step ensures the required tensile strength, resistance, and dimensional accuracy of the wires. The drawn wires are then subjected to the stranding process, where they are twisted together using high-speed stranding machines to form conductors. These conductors are also compacted to reduce AC losses, thus improving energy efficiency. The insulation process follows, where conductors are coated using a state-of-the-art CCV, continuous catenary vulcanization extrusion line. This system operates in a clean environment with filtered air and positive air pressure to prevent any contamination. A German-made online cross-section monitor ensures uniformity and precision in insulation. For multi-core cables, the insulated wires are then twisted and laid up using advanced drum twister machines, which prevents stress on the insulation layers. This minimizes the risk of void formation and enhances the durability of the cables. The twisted cores are bound together with an inner PVC sheath using computerized extrusion lines, which not only holds the cores in place, but also acts as an extra moisture barrier. Next, the cables undergo the armoring process, where a protective layer of aluminum or steel is applied. A uniform zinc coating is used to provide corrosion resistance, ensuring the cables remain rust-free and mechanically protected. Following this, the cables are coated with an outer PVC sheath using modern sheathing machines. Notably, Havells manufactures its own PVC compound in-house, enhancing quality control and flame retardant properties. The plant places a strong emphasis on testing and validation. ANABL accredited laboratory and a DSIR recognized technology center carry out more than 30 different tests covering physical, mechanical, electrical, thermal, chemical, and fire-related parameters. Every cable is tested for conductivity, flame resistance, oxygen index, smoke density, and thermal stability to ensure compliance with stringent safety standards. In the final phase, the cables and wires are coiled, measured, and labeled using modern machines. Flexible cables in particular undergo a double-layer PVC insulation process, with a virgin PVC inner layer and a thin-colored outer layer to maintain insulation resistance while offering aesthetic appeal. The upcast process is a vertical continuous casting method used to produce oxygen-free copper, OFC rods, known for their exceptional electrical conductivity and purity. In this process, high-purity copper cathodes are melted in an induction furnace under a protective atmosphere to prevent oxidation. The molten copper is then cast upward through graphite molds, which are water-cooled to solidify the metal into rods as it rises. The rods are typically produced in diameters ranging from 8 mm to 30 mm, depending on the application. Because the casting is done in an oxygen-free environment, the resulting copper rods contain minimal oxygen content, typically less than 10 ppm, which enhances conductivity and improves resistance to hydrogen embrittlement. The OFC rods produced are ideal for fine wire drawing, enameled wire, and high-frequency or signal transmission cables where high conductivity and low signal loss are critical. The upcast process also allows flexible production volumes and quick alloy changes. Continuous cast rolling line for FRHC rod detailed overview. The continuous cast rolling CCR line for fire-refined high conductivity FRHC copper rod is a highly efficient and widely adopted process for producing electrical-grade copper rods used in wire and cable manufacturing. Unlike the upcast process, which is primarily used for oxygen-free copper, the CCR method utilizes molten copper derived from fire-refined scrap or cathodes, offering a more cost-effective approach for high-volume rod production. The process begins with charging fire-refined copper scrap or cathodes into a shaft furnace or reverberatory furnace, where the material is melted at temperatures above 1,100 degrees Celsius. The molten copper is often subjected to refining treatments, including deoxidation using phosphorus-based additives to improve conductivity and casting properties. Once refined, the molten copper flows into a casting wheel, or a continuous casting machine, typically composed of grooved copper molds mounted on a rotating wheel. As the copper fills the grooves, it begins to solidify while being continuously withdrawn and cooled by water sprays or baths. This forms a long, semi-solid copper bar, known as a cast bar or strand. The cast bar is immediately fed into a series of multi-stand rolling mills while still hot. These mills progressively reduce the cross-sectional area of the bar, transforming it into a round rod, usually 8 mm in diameter. The rolling process is carried out without reheating, maintaining energy efficiency and metal integrity. The bright annealing process involves heating copper wire in a controlled, inert atmosphere, restoring ductility after drawing while maintaining a clean, shiny surface free from oxidation or discoloration. The paper insulation process involves wrapping copper or aluminum conductors with layers of high-quality electrical-grade paper, such as kraft, crepe, or thermally upgraded paper. This process is typically used for transformer windings, oil-filled cables, and high-voltage applications where superior dielectric properties are essential. The paper is applied in a spiral or longitudinal manner, using specialized taping machines to ensure uniform coverage and consistent thickness. Multiple layers may be applied depending on the voltage rating. After wrapping, the insulated conductor is often dried and impregnated with insulating oil or resin to enhance thermal stability, moisture resistance, and electrical insulation performance. The red lab/testing refers to a specialized quality control and testing area, often focused on copper-based, hence red, conductors. Here, samples from various production stages undergo mechanical, electrical, and chemical testing to ensure compliance with industry standards. Tests typically include conductivity, tensile strength, elongation, resistivity, and surface finish evaluations. The lab is equipped with precision instruments like micrometers, tensile testers, and resistance meters, playing a critical role in maintaining consistent product quality and ensuring wire reliability in electrical applications. The aluminum RBD rod breakdown process is used to convert large diameter aluminum rods, typically 9.5 mm, into smaller wire sizes suitable for electrical applications. The rod is drawn through a series of tungsten carbide or diamond dies using a multi-stage wire drawing machine, progressively reducing its diameter while increasing length and tensile strength. To prevent wire breakage and ensure surface quality, lubricants are applied during the process. After drawing, the wire may undergo annealing to restore ductility. RBD aluminum wire is commonly used in power transmission lines, cables, and electrical wiring due to its lightweight and good conductivity. The 7-bobbin skip refers to a specific configuration in a skip stranding machine, used to manufacture multi-strand electrical conductors. In this setup, 7 bobbins, each holding a reel of wire, are mounted on a rotating stranding cage. The machine twists these individual wires together in a skip-lay pattern, meaning the stranding skips over certain positions to reduce torsion and improve flexibility. This method is ideal for creating flexible, round conductors used in cables requiring frequent bending or vibration resistance. The skip strander provides better strand geometry, reduced conductor resistance, and improved circularity. The result is a uniform, mechanically stable conductor suitable for power cables, control cables, and flexible wiring in industrial or automotive applications. The process ensures high-speed, consistent production of multi-wire strands.